Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight are two of our students who I will let say hi and introduce themselves. And we'll start with the man captaining the spaceship next to me.
This is my X-Wing. I'm Eli. I'm a physics and astronomy student here at UMD.
And I'm Rachel. I'm a biology and environmental science student here at UMD.
So, tonight's show is a really fun one, kind of taking a look at how we know things that are usually kind of taught as just fact, like the speed of light. But obviously, we haven't known that for eternity. We had to figure it out somehow. And so the show is going to explore how we figured out all of these things that we take as known facts today. Eli is going to be leading our show tonight. And before I fully hand it over to him, as always throughout our shows, if you have any questions, feel free to leave them down in the comments. I will be keeping an eye on those and will let Eli know as questions pop up. If we don't get to it right away, don't worry, we will have time at the end to answer questions as well. All right, with that, Eli, it is all yours.
Awesome. Let me get the screen share.
You muted, Eli.
Oh, oopsie. How does the screen look?
Looks good.
Okay, sweet. Something funny I just noticed. If you look in this young gentleman's hand, you can see he's holding what appears to be a TI-83.
Oh, yeah.
An old Texas Instruments calculator that I used in high school. That's kind of funny. Okay, but yeah, as Jessica said, this is How Do We Know, where we'll just kind of take a look at how scientists throughout history have figured out some of the things that we just kind of take for granted uh, in astronomy. Now, this is quite the opening slide here, but I think it's a little important just to get a little bit of a basis for how these discoveries were made before we dive in, because trigonometry is extremely important to astronomy. And it all depends on right triangles. So on a triangle, on a right triangle, that is, you've got the adjacent side, the opposite side, and the hypotenuse. And those are relative to the angle that you're measuring. So if you're measuring this angle here, denoted by, this is called theta, that's just the degrees of the angle. If you're measuring this angle right here, this would be the adjacent side, this would be the opposite side, and this would be the hypotenuse. And these trigonometric functions are just ways to relate the length of the sides of the triangle to the measure of that angle right there. So for example, the sine of this angle right there is equal to the length of the opposite side divided by the hypotenuse. For cosine, it's the adjacent side divided by the hypotenuse, and the tangent is the opposite side divided by the adjacent side. We really won't need to do any calculations throughout this show, thankfully, but I feel like it's just kind of important to get an understanding for how they figured these things out and what the underlying math they were using is. So the first thing I want to talk about is, how do we know the size of the Earth? So the size of the Earth is a well-known size nowadays due to the advent of space telescopes and their ability to take images of the Earth. But previous to space telescopes, it took some very clever experimentation around 250 BC by Greek astronomer and scientist Eratosthenes to get a good idea just how big our planet was. He knew that on the day of the summer solstice, the sun cast no shadow at noon in the city of Syene, which means it lies directly on the Tropic of Cancer. He wanted to see if the same could be observed in Alexandria, a city quite some distance away. So he traveled to Alexandria and put a post on the ground to see if a shadow was cast. To his surprise, a shadow did appear. So Syene right here would be the Tropic of Cancer. He moved all the way to Alexandria, and as you can see, the incident sunlight here cast a shadow off of the pole he stuck in the ground. And he measured the angle between the post and the shadow to be about 7.2 degrees. through some trigonometric rules and the assumption that the Earth is perfectly spherical, which it isn't, but it's pretty close. Eratosthenes reasoned that Syene and Alexandria are 7.2 degrees apart on the circumference of the Earth. If they are 7.2 degrees apart, and 7.2 is 1/50th of the circumference of a circle, then the distance from Syene to Alexandria by extension must be 1/50th of the circumference of the Earth. So he actually had someone walk from Syene to Alexandria, which is no small task, and multiply that by 50, and he found out how big around the Earth is. And he found it to just under 1% off from the real value. He calculated about 80,000 kilometers. The actual value is about 80,060 kilometers. So very impressive, like almost frighteningly close for the time. The next really cool thing that was discovered using and kind of building off of Eratosthenes' discovery was the size of the moon. So Aristarchus of Samos, around the same time, knew that the size of the Earth would be an invaluable tool in calculating other things, like celestial objects. So Aristarchus correctly reasoned that a lunar eclipse was the result of Earth casting a shadow onto the moon, but incorrectly reasoned that the sun's light reaches the Earth in perfectly parallel lines. So I'm trying to illustrate that in this image here. So Aristarchus of Samos reasoned that this was the kind of a good drawing of the situation, when in reality this is a better drawing of the situation. And neither of them are great drawings because I did them in Google Drawings. But I think it gives you an idea for what the reasoning was and what the flaw was. The sun's light, pretty much as I said, it doesn't reach the Earth in parallel lines, which would stand to reason that somehow the sun was comparable in size to the Earth, which we know it's not. It casts a shadow that is smaller back here than the actual diameter of the Earth right there. But ignoring this discrepancy, Aristarchus first timed the period in which the moon was within the Earth's shadow during a lunar eclipse, which turned out to be 2.6 hours. And he then timed the period it took for the moon to travel one of its own diameters in the sky, which came out to be roughly an hour. And knowing those two numbers, he reasoned that since it took the moon 2.6 times longer to travel the size of the Earth than itself, the Earth must be 2.6 times bigger than the moon. And he then found that the diameter of the moon to be about 38% of Earth's. Now, taking into consideration the fallacy in his logic, he was off by about 8% in his estimation. But given the time and the tools at his disposal, 8% error is remarkable. And you're going to hear me say that a lot during this program, but it really is just kind of jarring how accurate they were, given that they didn't even have telescopes. So just very impressive. The moon is about 30% of the size of the Earth, whereas Aristarchus of Samos said that it was somewhere around 38%. How do we know the distance to the moon? So after Aristarchus discovered the size of the moon, Hipparchus used this as a stepping stone towards discovering the distance to the moon from the Earth, which is also very important, as you'll see in the next slide, or the second next two slides. This one is probably the most mathematically intensive and impressive, and I have to constantly remind myself that these calculations and discoveries were made 2,200 years ago. So to find the distance, Hipparchus realized that as you move across the surface of the Earth, the apparent position of the moon in the sky changes relative to the stars behind it. This is extremely useful in finding this distance, as you're using something called the Parallax Method, which is widely used throughout astronomy to find the distance to, in this case, the moon, to stars, very far away things. So what you're seeing in this image is, if you're on one spot on the Earth and then you take an extremely long walk to another spot on the surface of the Earth, you would see this background star change position relative to the moon's position. And you can use that to carry out the parallax method. So with the two apparent positions of the stars, you can draw a triangle connecting two different places on the Earth's surface at the moon, which I've done in this illustration. You can then find one angle of the triangle, which is all you would need, by measuring the distance between the stars in the sky. Hipparchus found that angle to be 0.3 degrees, and he also knew the distance between Celzes in the United Kingdom and Athens, Greece, which are the locations from which he looked at the star relative to the moon. By doing some trigonometry and solving that triangle, he found the distance to the moon within 17% of the actual value. Not extremely precise, but again, extremely impressive, especially taking into consideration, the margin of error in the previous calculations. So now we have a lot of really good tools at our disposal. We know the size of the moon, we know the size of the Earth, we know the distance to the moon, and naturally, I think the next couple discoveries should involve the sun. So how do we know the distance to the sun? So after this, Aristarchus again took the reins and wanted to use the distance to the moon to find the distance to the sun. Like all others before him, he used trigonometry and triangle identities to his advantage, which were kind of invented around this time for this purpose. The great minds at this time period, I don't know. I like to imagine that they treated it more as like a friendly competition to see who could discover cooler stuff. And I think Aristarchus won. If we're taking this one into consideration. But they actually had to invent math to make these calculations. Hipparchus is kind of credited as being like the father of trigonometry. What Aristarchus did is he constructed a kind of hypothetical right triangle out of the moon, sun, earth system. And he reasoned that this was okay because when the moon is half illuminated, which we would call a quarter phase, probably first quarter, it's making a right angle. So you can see here, the sun's light is going to hit the moon and illuminate this half. I hope that it looks clear enough on the screen. It's going to illuminate this half of the moon, which to us looks like this part is illuminated, which is what we call first quarter. He, kind of constructed this hypothetical right triangle. And given that he could find the distance between the sun and the moon in the sky, or find the angle between them, which he found to be 89, or he found it to be 87, but it's really closer to 90, but he was extremely close. He then used the distance to the moon to calculate the hypotenuse of the triangle. And he found it to within 14% accuracy. And for naked eye astronomy, that is absolutely remarkable. I mean, just the simple task of estimating the angle between the sun and the moon using naked eye is pretty impressive. So now that we know the distance to the sun, we can find the size of the sun. If the Earth were any closer or further from the moon and the sun, solar eclipses wouldn't look like they do. And in fact, this happens sometimes. If we get certain celestial alignments where the moon is a little bit closer to the Earth than it usually is, you get what's called an annular eclipse, which is where you can actually see the outside ring of the sun. The moon doesn't cover the whole thing perfectly. But luckily for us, a lot of solar eclipses are positioned just correctly that the moon just barely blocks out the entire sun. And if our solar system had formed in such a way that this alignment didn't happen, we kind of would have been out of luck for this this calculation. So Aristarchus thought that he could use this perfect alignment to his advantage, and he drew a diagram not unlike the one seen right here, and realized that the moon and the sun have the same angular size in the sky, which means that when we look at the moon and the sun in the sky, they appear to be the same size, which is why the moon can block out the entire sun during a solar eclipse. Because of this, Aristarchus found that we could apply some rules we know to be true about similar triangles, and discovered that the size of the sun could be found through the ratio shown below the diagram. So the size of the sun divided by the size of the moon is equal to the distance to the sun divided by the distance to the moon. We now know these three values so we can just solve for the size of the sun. So the error on this one was a little bit larger than some of the other ones, but kind of the virtue of this calculation is that Aristarchus found that the sun is much larger than the Earth, which we now know to be extremely true. And that was a very important concept to astronomy. And, even I would say the development of gravitation, cosmology, things like that. Just kind of mapping out and getting a feel for the size of celestial objects was pretty new. And the fact that Aristarchus was able to show us that the sun and later on by extension other stars are much bigger than planets, it's a good foundation for the future of astronomy and physics. Also, we would have probably not had theories put forth that Earth orbits the sun and things like that, which are pretty important. So this next one is probably my favorite, as it happened almost completely on accident. So some 1500 years after the time of Aristarchus and Hipparchus, the first attempt to prove that light travels at a finite speed was by Galileo Galilei, and it consisted of two men with lanterns standing on hilltops separated by less than a mile. You can probably imagine how that turned out. And it was apparent that a new method was needed to prove the idea that light didn't travel instantaneously. As it happens, light travels extremely fast, too fast for the reaction time of two men on hilltops to keep up with, but it's not instantaneous. So Ole Romer, the gentleman on the left here, was not attempting to prove the speed of light when he was measuring the time it took for Jupiter's moon, Io, to orbit the planet one time, but he kind of stumbled upon it by accident. He noticed that when the Earth was at its farthest distance from Jupiter, the orbit of Io appeared to be 11 minutes longer than the average orbital period, and when Earth was at its closest distance, it appeared to be about 11 minutes shorter. He reasoned that this was due to the fact that the light coming from Io traveled at a finite speed, and this discrepancy was due to the travel time it took for the light to reach Earth at these points. So kind of the interpretation of that is, so you would see Io, eclipsed by Jupiter, or well, you would see it, come out of the other side of Jupiter's shadow, from the other side of Jupiter, and you would just start to see some light as it, reached that shadow. And when Earth was here, you would see it 11 minutes earlier than when Earth was there. So Ole Romer reasoned that that 11 minutes was due to the travel time from here. Well, actually, it would be 22 minutes from here to there. So from here, famous astronomer Christian Huygens measured the speed of light and found it to within 70% accuracy. Now, again, not extremely accurate, but a lot better than us sitting there thinking that light traveled instantaneously when it certainly does not. Nevertheless, this speed was confirmed with more accuracy some 50 years later by astronomer James Bradley using an effect called stellar aberration. So we're going to talk about the parallax method a little more, but we'll talk about it now in respect to how we find the distance to nearby stars. So this method used to find the distance to the moon by Hipparchus lives on, as it is the primary method of finding the distance to nearby stars in our galaxy. It's called stellar parallax when used for stars, and scientists and astronomers adopted Hipparchus's method by observing how nearby stars appear to move relative to the stars behind them during Earth's orbit around the sun. So remember back to Hipparchus, he walked across the surface of the Earth to see how the background changed relative to the moon. Nearby stars are a lot further away than the moon is, so you need to move across the surface, quote unquote, a lot more. And in the case of stars, we actually use the distance around the sun in Earth's orbit as our kind of travel. So after 6 months, the star's position appeared to have changed significantly, and this distance can be measured to give you the parallax angle P. And once you know that angle, you can calculate the distance to the star, because we know the distance now between the sun and the Earth. So 6 months later in the year, Earth has moved halfway through its orbit. It's on the other side of the sun. And you get this kind of angle between the backgrounds. You can, find this parallax angle P and then solve this triangle right there for the distance to the star from Earth. Another really interesting one, how do we know how far away galaxies are? So for distances much larger than stars within our galaxies, like distances between galaxies, parallax doesn't work, as the parallax angle made by Earth orbiting the sun is way too small to be measured. And if you have the same thought as I did, which is, well, why don't we wait as the sun goes around the Milky Way? That takes a really long time, much longer than we could do in a lifetime. So I believe actually they say like the last time Earth was where it is now in like respect to the center of the galaxy, the dinosaurs were walking around. So kind of a minute. So we have to use a different method, and we use what are called standard candles. So standard candles are any stars or astronomical events that have a known brightness and can be identified from far away. So if astronomers know how bright the object actually was, or how bright the event actually was, and they see how bright it appeared to be, they can calculate the distance. The brightness of something decreases with what's called the inverse square law. So basically, if you go twice as far away, it's 1/4 as bright. So the brightness, how many times further away you are squared. So like I said, if you're twice as far away, it's 1/4 as bright. If you're 3 times as far away, it's 1/9 as bright. So we can pretty simply just solve this for distance. And the last slide, how do we know where black holes are? So something often glossed over when talking about black holes is how we detect them. And it's actually really interesting. So if you think about it, a black hole is fundamentally really hard to find. It gives us no light to see it or identify it by. Sometimes we get lucky and there's an accretion disk around the black hole, but you need very powerful telescopes and highly sensitive astronomical instruments to find those. We use a different method, a kind of logical reasoning. So black holes are commonly found by observing the things around them. If we watch this video, it appears that these stars are orbiting an invisible center of mass, and a strong one at that. In a period of 10 years, it pulled multiple stars around it with extreme force. So there's only one thing we know of that can do that, and in this case, it was the black hole at the center of the Milky Way. So I'll play the video and you'll see. On the crosshair, we've got some unidentified, mysterious center of gravity or center of mass that's just whipping these stars around it at insane speeds. And we reason that since we don't know of anything in the universe that can do that other than a black hole, it's probably a black hole. The stars about it in highly elliptical orbits, and through this footage, scientists were able to infer the existence of a black hole. So let's watch it one more time because it's pretty cool. You can also see how long it took for this footage to be taken. So it started in 1992. And, we go to 2000, how far is it? Like 2006, which is pretty cool. Yeah, that's how one of the ways we infer the existence of black holes in various spots. So that's all I got. With that, I'm going to stop sharing.
Very cool.
I forgot I was in my X-Men.
Yeah, it's always so. I'm always fascinated by how they were able to figure these things out.
I think people were just a lot smarter than we are now.
Well, or at least, you had to think in different ways. Am I back?
Yeah.
Okay.
Who just...
Am I back? I think I'm back. I think I'm good. Okay.
Yeah, you're good. At least from my end.
Yeah, no, I think I may have been dropping some frames there. So if you got a little stutter in the show, that's my internet acting up. I apologize for that. But yeah, just, I mean, they had to think differently. We have different tools and devices, and they
Yeah.
didn't. And it's just really clever what they're able to come up with.
Yeah.
So we did get one question, not entirely related, but it was back when we were talking about the solar eclipse and how, you know, the moon is sometimes a little closer, a little further. We have terms for those called apogee and perigee. So perigee is when you're a little bit closer to when the moon is at its closest to the Earth, and apogee is when the moon is at its furthest from the Earth. And the question was, does anyone have a mnemonic or device or way of remembering which is which? Because I will be honest, when I saw the question asking about a mnemonic or way of remembering, I Googled because I could not remember which was which.
Yeah.
So I didn't know if anyone else.
Nope. I Google it.
Pretty much, yeah, I Google it.
Interestingly enough, we don't really see those terms very often in like classes.
No.
So I mean, I haven't had to really know them in terms of like courses. I mean, obviously in like astronomy vocabulary and stuff, we knew them, but yeah.
Yeah. Yeah, I would say I don't think I ever use the terms outside of the one time in class each semester that I teach it.
Yeah. We used it in classical mechanics a couple times when we were talking about like Kepler orbits.
Oh, yeah, that
But
makes
yeah, that's
sense.
about it. And when I encountered them, I Googled them.
All right. So we have a couple more questions that came in. How accurate is the math of different ancient cultures with their solstice monuments?
Yeah. That's a
Pretty
really good
accurate.
conversation to be had. The the striking one to me, and the reason I'm speaking to this one is probably because we have Jim here at the Planetarium, but Dakota astronomical predictions had like the moon cycle down to like some crazy like 97% accuracy like thousands of years ago until NASA got it like even closer in like 1950. So there are definitely some processes and some information that need to be investigated and given credit in different cultures that we don't give credit to right now, because we're all about Western science. And there's nothing wrong with Western science, but I think it's a disservice to other cultures to act as if we were the people that got it right first. It's absolutely not true.
And I will say this is a good kind of promo for next week. Gemrock is actually doing our show next Wednesday to talk about actually a lot of this with the Dakota and what they were able to predict, especially with the upcoming equinox. And they'll also be talking about the Mayans as well, and some similarities that appear to be between the two. I don't want to give too much away. So if you're interested, come back next week, next Wednesday for Gem Rock show. It's gonna be fantastic.
Yeah.
Another question: what happens when the black hole spins stars out of their orbits?
It's super cool. Sometimes what happens is the tidal forces on the star. So it's like if a star is close to a black hole, one side of the star is getting pulled a lot harder than the other side of the star. So as the star moves around, you can like see like some material will be like thrown off, and then the black hole will pull it back in, and they'll also just start eating material off of the star due to that tidal force. They'll just start pulling gas off of the star. And that's a way that we get accretion disks a lot. It's a lot of gas coming off of a nearby star, starts spinning around the black hole, and it gets heated up until it's crazy hot, due to friction between all of the gas molecules orbiting. And then it glows in X-ray, and then we point an X-ray telescope out, and we see this big glowing ring. A lot of cool stuff can happen.
And you can just also have the star just gets flung away.
Yeah, absolutely. Just gets like pulled elliptically out and then
slingshotted, basically.
See you later. Yeah.
Yeah. Which isn't really as dramatic as it might sound. Because I know, like, it's you might think of like, oh, it's gonna get flung out, so it's gonna start hitting things and ricocheting, and yeah, things in space are very far apart. So when this star, if and when a star gets flung by a black hole, it's probably not hitting anything. It's
Yeah.
just gonna get flung out. And will land in a new orbit around the center of the galaxy, depending on just how fast it was flung out.
And we're very spoiled too by our ability to speed up and slow down video. Because like that video that I showed, I mean, that took place over 15 years or something like that. I mean, these things don't happen like they show them in the movies, where it's like the star gets pulled and gets flung out right away. I mean, it takes years. So it's not, like Jessica said, it's not as dramatic as you would think it is, but it can be pretty dramatic depending on what's going on.
Let's see. I may remember this wrong, but if I remember correctly, for gravitational boosts in our solar system, when you pass a massive object inside the orbit, you get a boost. If you pass outside the orbit, you get deboosted, or you get kind of pulled in.
Wait, what?
I'm trying. So it's anytime you have a gravitational boost, one object is gaining energy and the other is losing. So it depends on, like, if you're doing this with a spacecraft, which side of the equation the spacecraft is on, whether it's going to gain the energy so it'll get flung away faster, or if it's going to lose energy and it will get slowed down. And that depends on the trajectory and everything going on. My physics brain is not working super well at the moment to give these specifics. I don't remember.
Well, I think it's like,
if it's inside, it gets pulled. No, so yeah, if it's inside, it gets pulled faster, which is going to give it energy and it'll move out. And if it's outside,
no,
isn't it still?
no, it would be, if it was inside the orbit, the object is going to pull it further away from the center of gravity, so it's going to start moving slower.
Yeah.
Yeah, so if it's inside, it loses energy. If it's outside, it gains energy.
No, I think it was inside boost, outside lose. Because this one's moving faster. No. Oh my god, my brain's not working right now.
Outside should gain energy, I think.
That's moving faster, so it's getting pulled. Yeah, which would speed it up, which would push it. And then that's moving faster. Yeah. Outside gets pushed out, inside gets, yeah. Yeah, that's right. Oh my goodness. It's been a long day. All right. Well, we will have, let's say, we'll take a few more minutes to see if any other questions come in. In the meantime, let me tell you what's coming up for our shows over the next week. So on Saturday, we are doing our Valentine show, Love is in the Stars, which is going to take a look at different constellation stories that all center around some type of love, whether it's romantic, familial, friendship, all of that. Next Wednesday, as I've already told you, Jim Rock is going to be doing our show and talking about Dakota and Maya astronomy. And then next Saturday is the kind of next edition of Ask an Astronomer, where we will be here to answer your questions and possibly get stumped. We'll see. All right, well, I'm not seeing any other questions at the moment. So I guess before I head off, I will make an unofficial announcement that's coming out a little later this week. We are planning on reopening for our private shows and field trips in March, and we are also hoping to be doing public shows by that time as well. We're not quite at the point that I can fully say it's going to happen at the beginning of March, but we are getting there. Everything is on track. It's just be on the lookout. We are welcoming people back, at least for private shows in March, hopefully for some public shows around then as well. So we are very excited. And we will get some fun new stuff to open with. But again, still fixing all the details. We'll announce everything. All right. So with that, I think we will wrap it up. Thank you everyone so much for joining us. If you enjoyed the show, we've been doing this for almost 2 years now, so we have a huge backlog of our past videos that you can find in the videos tab of our Facebook page or over in our YouTube channel, which is linked below, or linked in the video description. And we will be doing this for at least through February, every Wednesday and Saturday at 7 p.m. Central. March may change depending on if we do end up being able to open for public shows, but we'll let you know what's going to happen there. All right, I'm going to stop rambling. Thank you for joining us. Have a wonderful rest of your evening, and we will see you next time. Bye, everyone.